If you've ever found yourself completely lost in a maze of deeply nested classes, yeah, today is for you. Welcome to This Explainer. We're unpacking a massive, fundamental transformation happening right now in software architecture. For decades, pure object-oriented design has been the undisputed gold standard, right? But as our systems scale and grow infinitely more complex, modern software design is actually evolving beyond its traditional object-oriented roots. We're trying to build more sustainable, resilient systems. We're moving into a multi-paradigm world, and honestly, this shift is fundamentally changing how we write code. Okay, let's dive into this, because it challenges a core assumption many of us have held for literally years. Is pure object-oriented programming, and particularly our heavy reliance on class inheritance, is it really still the ultimate solution for code reuse and system design? As developers, we've basically been conditioned to build these deep, intricate family trees of classes to solve our problems. But as you'll see today, that default reflex might actually be holding our modern systems back. In fact, the source material explicitly highlights this shift, stating, programming languages are increasingly moving away from being pure object-oriented languages as our software design methodologies. And this isn't just some fringe opinion. This is a massive industry-wide shift. The very tools and languages we use daily are adapting, pushing us away from an exclusive reliance on pure object orientation and towards something much, much more flexible. To understand where we're going, we kind of need to ground ourselves in what object orientation actually is. Back in 1985, Cardelli and Wegner defined it simply. Object orientation equals data abstraction plus object type plus inheritance. The real powerhouse here, it's data abstraction. It's the brilliant separation between the definition of data and its, often messy implementation. Think of it like driving a car. You don't need to understand the exact thermodynamics of the combustion engine just to press the gas pedal, right? It allows us to interact with the system without needing to understand the complex, hidden mechanics operating underneath. But here is where we run into trouble. Objects are a double-edged sword. On one hand, they offer fantastic procedural abstraction. They act like these first-class modules that you can pass around flexibly. On the other hand, objects are highly dynamic entities with imperative states. Because an object's internal state is imperative, meaning its data can be unpredictably altered behind your back at runtime, verifying a program's correctness becomes incredibly difficult. You completely lose the strict, predictable guarantees of a static system. So this brings us to a really sharp contrast in how we design our object hierarchies: interface inheritance versus implementation inheritance. Interface inheritance is generally safe and it's incredibly useful. It's polymorphic, meaning objects can easily take on many forms and swap parts, and it's usually shallow, maybe just 2 or 3 layers deep. This creates highly flexible, replaceable objects. Implementation inheritance, however, which is often called code inheritance, is where things get messy. Creating subclasses just to inherit code implementation often makes the entire system rigid, brittle, and highly problematic to verify. Now, what's really interesting about this slide is how it perfectly captures that architectural hierarchy. We see a plausible scenario where interfaces sit nicely at the top, an abstract class in the middle, and concrete classes down at the bottom. But imagine if this wasn't shallow. Imagine a deep, sprawling tree of concrete classes. In that scenario, any minor change made close to the base ripples outward, causing completely unpredictable ramifications across all branches. The deeper the hierarchy, the more vulnerable the whole system becomes. This is exactly what we call the code inheritance trap. While inheritance was heavily touted as the ultimate path to code reuse, empirical studies have shown it often doesn't compete favorably with traditional modularity. Excessive use of objects and deep, rigid code inheritance trees leads directly to unnecessary software complexity. It creates maintenance nightmares rather than solving them. I mean, we've all been there, right? Crying over a broken build just because we tried to change one little base class method. It ends up permanently tying your high-level business logic to concrete, messy implementation details. So if deep class inheritance is a trap that leads to rigid code, how do modern systems actually escape it? Well, the answer isn't to just throw out object orientation entirely. Instead, it's to pivot toward a liberating, multi-paradigm approach. We are drastically reducing our reliance on traditional class inheritance by bringing in concepts from other programming philosophies. Just look at the tools we use every single day. Languages like Go, JavaScript, C#, Python, Ruby, these are currently dominating the industry. And they aren't pure object-oriented environments. They are multi-paradigm ecosystems. They intentionally blur the lines between procedural, functional, and object-oriented programming. They empower developers to pick the exact right tool for the specific job rather than forcing every single problem into a rigid class hierarchy. As the text beautifully points out, older paradigms are not replaced, they merge as one collective repertoire. Thinking in objects is simply a natural progression of thinking in modules, and now adding functional expressions and static types into the mix, that's the next evolutionary step. We aren't abandoning the past, we are seamlessly integrating it into a unified, much more powerful approach to problem solving. To really grasp this integration, think about the core difference between the old and the new. Traditional structural or modular design focuses heavily on the static behavior of a system, what the code structurally is. Object-oriented design, on the other hand, captures the dynamic behavior, how the system changes and interacts at runtime. Multi-paradigm design is the breakthrough that successfully integrates both, allowing static and dynamic behaviors to coexist and actually complement one another. One of the absolute most powerful ways we see this integration and exactly how we reduce our reliance on class inheritance is by injecting higher-order functions into our object-oriented designs. In functional programming, passing functions as parameters is just standard practice. When applied to objects, these higher-order parameters act as hook points. It's almost like leaving a blank space in a recipe so you can add your own custom spices later. They allow us to achieve polymorphic behavior without ever having to construct a rigid inherited subclass. Let's walk through how this looks in a modern language like JavaScript. Instead of creating a base record class and then a custom record subclass just to override a save method, you define a core process, like save record. Then you simply pass custom functions, like before save or after save, directly as parameters. The system executes this custom logic dynamically. This empowers developers to deeply customize behavior on the fly, completely bypassing the need for complex, rigid subclasses. It's a real game changer. And this brilliantly illustrates how modern language features are actively diluting the boundaries between paradigms. Lambda expressions allow us to quickly associate data with dynamic behavior. C# extension methods let us add new behaviors to existing types without touching inheritance at all. And Go? Go has exploded in popularity precisely because it prioritizes strict static typing and multi-paradigm support while largely sidelining traditional inheritance. The lines are totally blurred now. This multi-paradigm shift isn't just happening at the code level, by the way. It's practically mandated by the reality of modern software architecture. Today's applications aren't monoliths. They are a system of systems. A single business process might integrate legacy mainframe computers, modern web clients, and a dozen different cloud-based microservices. You simply cannot model that level of heterogeneous complexity cleanly using only pure object-oriented design. Let's move to and see how this builds visually in this data flow diagram. Notice the integration here. We have traditional static processes moving data from one store to another, but they are intertwined with object channels mapping to type A and type B. It perfectly shows how we can take classic, statically structured data flow diagrams and seamlessly weave dynamic business objects into them to handle specific behavior. It's the absolute perfect marriage of static modularity and dynamic object orientation. Ultimately, if we want to build sustainable systems that can survive years or even decades of changing requirements, we absolutely have to change our architectural habits. We need fewer layers of rigid application code and significantly reduced code dependencies, which means far less implementation inheritance. We need to lean into service-focused frameworks and structural connectors that prioritize interoperability. Taming the complexity of a system of systems requires a robust, flexible mixture of technologies and paradigms. So, the crucial point is this. Paradigm neutral is the new norm. When you start your next design, don't automatically default to a sprawling class hierarchy. Instead, start by analyzing the domain to understand the dimensions of commonality and variability. Figure out what changes and what stays the same. Then, choose the paradigm, whether it's functional, procedural, or object-oriented, that perfectly balances and encapsulates those specific constraints. Which leaves us with a final thought to reflect on as you go back to your own code bases. Ask yourself, are you relying too much on rigid inheritance out of pure habit? Is your codebase suffering from the code inheritance trap when a simple functional hook or a paradigm-neutral approach could make it infinitely more sustainable? The tools to build better, more flexible systems are already in our collective repertoire. I think it's time we fully embrace them. Thanks so much for joining me for this explainer, and keep questioning those design defaults.